Till here, we have discussed trigonometric ratios and identities, and we have solved some questions regarding that, and we have discussed measurement of angles also, degree measure and radian measure. We have done questions like if you're given the value of sine theta is equals to 1 by 2 and we need to find the value of tan theta. We have done such kind of questions. We make a right angle triangle. Let's say this angle is theta. Since sine theta equals to p by h, so we put here p equals to 1 and h equals to 2. By applying Pythagoras theorem, we get b equals to under root 3. So from here, we can say that value of tan theta is equals to p upon b. P is 1 and b is root 3. Now suppose if I ask you that the value of sine theta is given to you as minus 1 by 2 and we need to find the value of tan theta in this case. So how will you explain this? Since sides of triangle cannot be negative, therefore this situation cannot be explained using the concept of triangle. It can be explained using the concept of circle. So basically trigonometric ratios are circular functions. So let's talk about the real definition of these trigonometric ratios. So we are going to discuss over here now the real definition of sine and cosine function. Real definition of sine and cosine. Let's say we have a circle. We divide the circle into 4 quadrants with the help of x-axis and y-axis. This is x, O, x dash. This is y, O, y dash. Now let's say P is a point on the circumference of the circle with radius r. And this point P makes an angle theta. This point P makes an angle theta with the positive direction of x-axis in the anti-clockwise direction. So if I drop a perpendicular from this point P, on x-axis, let this perpendicular meet the x-axis at the point M. Then this triangle OPM. This triangle OPM is called as triangle of reference. For the point, this triangle OPM becomes the triangle of reference for the point P. So for any such point, to obtain the triangle of reference, what you need to do is drop a perpendicular from the point on the x-axis, mark that point, and the triangle OPM will give you the triangle of reference with respect to that particular. So we were talking about the definition. The definition of sine theta will be equals to algebraic distance of point P from x-axis. Algebraic distance of point P from x-axis upon radius of circle. This is the actual definition of sine theta. And similarly, the definition for cos theta would be equals to algebraic distance of point P from y-axis upon radius of circle. This is the actual definition of the function sine and the function cosine. So let's say if this distance is PM is y units and this distance OM is x units. If distance PM is y units and distance OM is x units and the radius of this circle is small r, OP. The radius of this circle OP is small r. So from there we can say that sine of theta will be equals to algebraic distance of P from x-axis. Algebraic implies that we need to mention the conventions. We know that if we go above x-axis, then we take a positive value. If we go below x-axis, we take a negative value. Similarly, if we go on right side of y-axis, we take a positive value. and if we go on left side of y-axis, we take a negative value. So here we need algebraic distance of P from x-axis. So the algebraic distance of P from x-axis is Pm. But this distance is above x-axis, so we will take plus y. We will take plus y upon radius of circle, which is r. To write cos theta is algebraic distance of P from y-axis. So this distance OM is given to us as x, and if I draw perpendicular from P on y-axis, let's say this point Bn, then Pn will be the algebraic distance of point P from y-axis, but here OM and Pn will be equal, so it will be equals to x. But again, this x is on the right side of y-axis, so I will take plus x. So cos theta will be plus x upon r. Is that clear? So this is how we will write the values of sin theta and cos theta from now onwards. Let's take some more examples. We are given the circle. We are dividing it into 4 quadrants with the help of x-axis and y-axis. Let's say this is x, O, x dash. This is y, O, y dash. If P is a point, here. Now this point P can move anywhere on this circle. So let's say this point is here, P point. So to obtain the value of sin theta or the angle corresponding to this point, what will I do? I will join P with O. So this particular angle measured in anti-clockwise direction from x-axis, the positive direction of x-axis. This particular angle which is measured from positive direction of x-axis in anti-clockwise direction. Let this angle be beta. If this angle is beta, so I need to find the value of sin beta and cos beta, let's say. So for finding the value of sin beta or cos beta, we need to make the triangle of reference. So how to make the triangle of reference? For making the triangle of reference, we need to drop a perpendicular from the point on x-axis. So I need to drop the perpendicular from this point on x-axis. Let it meet the x-axis at the point M. So this is PM. Let's say PM is y units and MO is x units. But we know the definition says sin theta is algebraic distance of the point P from x-axis. Now we are moving below x-axis. So this distance will be actually minus y because we need algebraic distance of this point from x-axis. It is below x-axis, so this y will be minus y upon r. Let's talk about cos beta. For cos, we need perpendicular distance of point P from y-axis, which is Pn. But we know that Pn will be equals to OM, and we are moving in the direction which is left of y-axis. So we need to take this x as negative because we are in the negative direction of x-axis. So it will be minus x upon r. So sin beta will be minus y by r and cos beta will be minus x by r. So from here we can say that we were given that sin theta was equals to minus 1 by 2. So we can say that theta may lie in third quadrant. We have divided this circle into 4 equal partitions. This was first quadrant, this is second, this is third, and this is fourth quadrant. So if sin theta is giving a value which is negative, so we can say that theta may lie in the third quadrant, because from here we can see that sine of an angle beta, which is actually in the third quadrant, gives you a negative value. So this is how we can explain the negative values of trigonometric ratios. Now let's try to find out the signs of trigonometric ratios in different quadrants. Signs of trig ratios. We have divided the circle. into 4 equal partitions with the help of x-axis and y-axis. Let's say this is x, this is O, this is x dash, x dash, this is y, this is O, and this is y dash. So for a point P, making an angle theta with the positive direction of x-axis in anti-clockwise direction, we draw a triangle of reference, say OPM. Let's take this unit as y and this as x. PM equals to y and OM equals to x. So we know that sin theta is equals to y upon r, perpendicular upon base. Cos theta will be equals to x upon r, perpendicular upon hypotenuse, and this is base upon hypotenuse. Tan theta will be equals to perpendicular upon base, that is y upon x. Then reciprocal of sin theta, that is cosec theta, will be equals to r upon y. Similarly, sec theta, reciprocal of cos theta, will be r upon x, and cot theta, reciprocal of tan theta, will be x upon y. So these were the trigonometric ratios. Now we need to find the values of these trigonometric ratios in the 4 quadrants. So by drawing these perpendicular lines, this is x, this is O, this is x dash, this is y, this is O, this is y dash. We know that this quadrant is the first quadrant, this is the second quadrant, this is the third quadrant, and this is the fourth quadrant. Now we know that in first quadrant we are going in right direction of y-axis and above x-axis. So x is also positive and y is also positive. So in all the trigonometric ratios, we know that r, which is a positive quantity because it represents the radius of circle. So we need to consider only x and y. Since x and y both are positive, all the trigonometric ratios are going to give you positive values. So in this case, in the first quadrant, all trigonometric ratios are positive. All trigonometric ratios are positive. Let's talk about the second quadrant. In second quadrant, we are again above the x-axis but in the left direction of y-axis. So in this case, x will be negative but y will be positive. So all those trigonometric ratios which involve only y will be positive. So y is there in sin theta and cosec theta only. So in the second quadrant only, only sine and its reciprocal cosec are positive. In the second quadrant, sine and its reciprocal cosec are positive. Let's talk about the third quadrant. In the third quadrant, we are below x-axis and in the left direction of y-axis. So x will be negative as well as y will be negative. So to obtain a positive quantity, we need to take the trigonometric ratios in which x and y both are available. So the trigonometric ratios tan theta and cot theta are such trigonometric ratios in which y and x both are available. So in the third quadrant, tan and cot, tan and its reciprocal cot are positive. Tan and cot both are positive. Similarly, in the fourth quadrant, we are below x-axis but in the right direction of y-axis. So we know that x is positive and y is negative. So for all those trigonometric ratios in which x is there, that is cos theta and sec theta, they will be positive. So in the fourth quadrant, cos theta and its reciprocal secant are positive. So in the first quadrant, all trigonometric ratios are positive. In the second quadrant, sine and cosec are positive. And in the third quadrant, tan and its reciprocal cot are positive. In fourth quadrant, cos and its reciprocal secant are positive. To remember this, we can have a short trick just to memorize this thing. Just draw a diagram. Just draw the quadrants. Mark the quadrants first, second, third, fourth. Write down the initials. A for all, S for sine and its reciprocal, T for tan and its reciprocal cot, and C for cos and its reciprocal sec. And remember it like this. A, all, S, students, all students, 2, first, second, third, fourth, ASTC, all students, 2 cap. This is the trick by which you can remember the signs of trigonometric ratios. Now we will discuss the reduction formula. Reduction formula. Where to use reduction formulae? Reduction formulae are used to find trig ratios of larger angles like 120 degree, 330 degree, etc. Reduction formulae are used to find trigonometric ratios of larger angles like 120 degree, 330 degree, etc. So let's start with the angles of the form 90 degree minus theta, or you can say pi by 2 minus theta. 90 degree invariance can be written as pi by 2. Let's divide this circle into 4 equal partitions with the help of x-axis and y-axis. This is x, O, x dash. This is y, O, y dash. Let's take a point P. Let's join O and P. Let's say this angle is theta. So triangle of reference corresponding to P can be obtained by dropping a perpendicular from P on x-axis. Let this point be M. Let this distance be y and this distance be x. Now we know that since in a right angle triangle, if this angle is 90 and this angle is theta, this particular angle will be 90 degree minus theta. So the point corresponding to this angle 90 degree minus theta is P itself. So this is the triangle of reference we are going to consider. So our triangle of reference is triangle OPM. So here we know that sine of theta is equals to y upon r that we have studied earlier, and cos of theta is equals to x upon r. Now let's talk about sine of theta 1, or you can say 90 degree minus theta. Sine of 90 degree minus theta. So from here sine of 90 degree minus theta will be perpendicular upon hypotenuse. For 90 minus theta, perpendicular would be OM, and OM is in positive direction of x-axis. So I will write x only, and upon radius. But we know that x upon r is what? Cos theta. So from here you can say that sine of 90 minus theta is basically equals to cos of theta. So for example, if you are given sine of 70 degree, so you can treat it like this. It is sine of 90 degree minus 20 degree, and it will be equals to sine of 90 minus theta will be equals to cos theta. So here sine gets converted to cos, and this angle gets reduced to cos 20 degree. Sine 70 is equals to cos 20. Similarly, let's talk about cos. If we need to talk about cos 90 degree minus theta, so from here cos 90 degree minus theta would be base. Base is y, and it is above x-axis, so it will be plus y. So plus y upon r. But we know that y upon r is equals to what? Sine theta. So from here we can say that sine of 90 minus theta is equals to, cos of 90 minus theta is equals to sine theta. So for example, cos of 40 degree can be written as cos of 90 degree minus 50 degree. This is cos of 90 minus theta, which can be written as sin theta. That is sin 50 degree. So cos 40 is equals to sin 50 degree.